Section: Introduction. In this section, we discuss the impressive capabilities of large language models, LLMs, in various natural language processing tasks. Often, a simple prompt can effectively guide the model to perform as desired, utilizing knowledge gained during its pre-training. However, when it comes to personalizing LLMs with new user data that becomes available after the initial training, we face challenges. Adapting LLMs to this new data requires additional resources and computational power, especially when scaling to many users. We identify two main approaches for adapting LLMs to new data. The first is prompt engineering, where we integrate new data through the prompt. This method has limitations due to the model's context window, which can struggle with large amounts of information, particularly in data-rich formats like video and audio. Even when the context window is adequate, LLMs can show positional bias, affecting the quality of the output based on how documents are arranged in the prompt. Additionally, longer prompts lead to increased latency and computational costs, making this approach less practical for large-scale use. The second approach involves fine-tuning the model by adjusting its weights to include new data. While this method overcomes some limitations of prompt engineering, it introduces new challenges, such as high computational costs from training separate models for each user. Updating these personalized models as new data comes in is also complex and resource-intensive, often requiring offline updates that can make the model less current. Moreover, training models for users with limited data can result in lower quality outputs. To tackle these issues, we propose ComMer, which stands for Compress and Merge. This innovative approach learns to compress user data into a compact representation that effectively adapts the LLM. By spreading the training costs across all users, we eliminate the need for individual training processes. This results in reduced computational expenses, more efficient adaptation to new data, and improved quality for users with limited data. We evaluate ComMer on two types of personalization tasks: personalized skill learning, using datasets for tweet paraphrasing and personalized news headline generation, and knowledge-intensive question answering with the per-LTQA dataset. Our experiments show that ComMer balances quality and computational cost well in personalized skill learning, efficiently handling multiple documents within a limited token budget, with quality improving as the number of documents increases. However, in knowledge-intensive tasks, ComMer struggles to capture all the information from the documents, leading to a decline in quality as the document count rises. We also explore the effects of pre-training, generalization to new data, and different merging strategies, providing insights into the trade-offs and potential improvements for ComMer's design. In the related work section, we note that personalizing LLMs ranges from using user data as a knowledge base to personalized skill learning. Previous studies have introduced various methods to address personalization challenges, but many incur high inference or training costs. Concurrently, other approaches like pplug have attempted to compress user documents into prompts, but they face limitations in computational efficiency and capacity. In contrast, ComMer utilizes trainable embeddings with mean pooling, allowing for better integration of multiple documents while reducing interference. We also highlight that, despite improvements in context window sizes, processing long contexts remains resource-heavy. Our method builds on latent representation techniques to merge document representations, achieving further compression. Lastly, we discuss model merging strategies that enhance performance across tasks, noting that ComMer focuses on merging document representations rather than weights, allowing for dynamic input adaptation and overcoming limitations of existing model inventories. Section Summary. In this section, we discuss the challenges of personalizing large language models, LLMs, to new user data, highlighting the limitations of prompt engineering and fine-tuning approaches. We introduce ComMer, a novel method that compresses user data into a compact representation, allowing for efficient adaptation of LLMs while reducing computational costs and improving performance, particularly in personalized skill learning tasks. Section: Architecture. In this section, we present our proposed architecture. The process begins with a collection of user documents and follows three main steps. 1. Compression. We independently compress each document into a soft prompt. This is done using a frozen language model, which has trainable compression embeddings and LoRa weights. We append trainable compression embeddings to the input document and pass it through the frozen model. This model's language understanding helps reduce training costs. We also add a trainable LoRa adapter to fine-tune the model for compression. The output we extract comes from the last layer's representations of the compression embeddings. 2. Merging. We combine the compressed representations of all documents into a single soft prompt using mean pooling. This method has several benefits. The resulting representation's shape does not depend on the number of documents, which helps with context window limitations and computational costs. It is also order agnostic, meaning the position of documents does not introduce bias. Additionally, we can pre-compute and efficiently update the aggregated soft prompt as new documents are added. 3. Response generation. We input the aggregated soft prompt into the frozen language model to generate the desired output. For training, we assume a dataset consisting of examples where each example includes a set of documents, an instruction, and an expected response. We process each example by compressing the documents and then inputting the instruction and expected response into the frozen model, along with the aggregated compression. We use cross-entropy loss over the tokens of the expected response, only updating the trainable compression embeddings and LoRa weights while keeping the main model's weights unchanged. In terms of data, we represent a collection of documents using mean pooling, which is efficient for personalization tasks where user data changes over time. When a new document is added, we only need to process that document and incorporate it into the existing aggregated compression, avoiding the need to reprocess older documents and saving costs. We evaluate our method, ComMer, on 3 tasks, with examples provided in the appendix. For personalized skill learning, the user's documents are crucial for tailoring task performance. We focus on 2 tasks from the LAMP benchmark: personalized tweet paraphrasing, where we rephrase tweets to match the user's style, and personalized news headline generation, where we create headlines that reflect the author's style. We follow a user-based split for testing, ensuring that the test set includes users not seen during training. In knowledge-intensive tasks, the documents act as a personalized knowledge base. We need to retain information from these documents, sometimes verbatim. We use a dataset derived from per-LTQA, which is based on synthetic personal memories. We create examples by selecting a subset of memories along with a question and answer for each persona, with 27 personas in the training set and 5 in the test set. For pre-training, we extend an unsupervised auto-encoding task to a multi-document setup. In this setup, we reconstruct text from compressed documents, prefixing each document with its index and using a query to ask about a randomly selected document. We utilize documents from the Fine Web dataset, truncating them to 150 characters, and create a training set of 1 million examples. All models in our research underwent a pre-training phase of 1 epoch. For our experiments, we use Gemma 2B as the backbone for both the generator and the compressor, optimizing resource efficiency by sharing weights. The input to the generator combines the merged compressed documents and the embedded instruction. We use mean pooling for merging and experiment with different numbers of compression embeddings. As a baseline, we compare with prompt tuning, where we concatenate a soft prompt with the embedded documents and instruction. The number of embeddings in the soft prompt matches the number of compression embeddings in ComMer. Further implementation details can be found in our paper. Section Summary. In this section, we propose an architecture that compresses user documents into soft prompts using a frozen LLM with trainable embeddings, aggregates these representations through mean pooling, and generates responses based on personalized instructions. Our method efficiently updates the document set without reprocessing older documents, enabling effective personalization for tasks like tweet paraphrasing and news headline generation. Section: Metrics. In this section, we discuss the metrics used in our experiments. For the LAMP benchmark, we rely on Rouge-based metrics for tasks like tweet paraphrasing and personalized news headline generation. Our findings indicate that these metrics can be quite noisy, making it hard to draw clear conclusions. Therefore, we also include perplexity in our analysis alongside Rouge-L. Our results are supported by both perplexity and Rouge-L, although the latter shows more variability. Similarly, for the per-LTQA benchmark, we use both Rouge-L and perplexity metrics. When it comes to personalized skill learning, we trained various ComMer and prompt tuning models, adjusting the number of documents and embeddings. We found that the number of embeddings affects prompt length since they are direct inputs to the frozen language model. We observed a direct correlation between the number of documents and embeddings with model quality. For prompt tuning, more documents and embeddings lead to lower costs, but this relationship doesn't hold for ComMer regarding the number of documents. Notably, in the personalized tweet paraphrasing task, ComMer produced higher quality results with fewer resources compared to prompt tuning, especially within a token budget of 128. We believe that using more documents could further improve results, but our datasets are limited to 8 documents per user. We plan to explore larger datasets in future work. In knowledge-intensive tasks, the scenario changes significantly. Here, having just one document is optimal, as adding more can introduce irrelevant information. In typical retrieval augmented generation applications, multiple documents are retrieved, but we found that prompt tuning handles irrelevant information well, while ComMer does not. For ComMer, more documents lead to worse perplexity and Rouge-L results. Regarding pre-training, we aim to quantify its impact on ComMer and examine different pre-training datasets for the personalized tweet paraphrasing task. We pre-train on the fine web dataset and also on the training set of the personalized task, applying an extended auto-encoding task to pass tweets. Our results show that pre-training improves performance, but the choice of dataset has little effect on the final outcomes. In our experiments, we used the same number of documents for training and testing. However, in real scenarios, users may provide a different number of documents during testing. We explored how well ComMer generalizes to varying document counts. Our findings indicate that ComMer performs better when exposed to more documents than it was trained on, but performance drops with fewer documents. Interestingly, when trained with just one document, averaging compressions at test time still enhances performance, suggesting that deep neural networks operate linearly in latent space. We chose mean pooling for merging document representations to optimize token processing and update costs. However, this choice may affect quality. We explored 2 alternatives: concatenating document compressions, which increases token processing costs, and compressing the concatenation of documents, which raises update costs. Our comparisons show that concatenating compressions does not perform as well as vanilla ComMer, indicating that mean pooling effectively captures a user's tweeting style. Compressing concatenated documents yields slight quality improvements but incurs higher costs. Thus, we conclude that vanilla ComMer is the most cost-effective method for document representation and is better suited for retrieval-based strategies. We plan to investigate this further in future work. Section Summary. In this section, we analyze the LAMP and per-LTQA benchmarks using Rouge-L and perplexity metrics, finding that while perplexity provides clearer insights, both metrics reveal that ComMer outperforms prompt tuning in resource efficiency for personalized tasks. We also explore the impact of document quantity and pre-training on model performance, concluding that ComMer adapts well to varying document numbers and that mean pooling is the most cost-effective method for document representation. Section: Discussion. In this section, we introduced ComMer, a new and cost-effective method for compressing multiple documents. We compared our approach to an existing popular method called prompt tuning, which directly exposes large language models to document content. We found that merging compressions is helpful for personalized skill learning tasks but less effective for knowledge-intensive tasks. This difference makes sense. In personalized skill learning, A single document usually doesn't contain all the information needed to understand a user's style. Instead, each document offers various style suggestions. By combining these suggestions from multiple documents, we can identify the styles that best represent the user's overall style. When we average the compressions, we reduce the unique features of each document, leading to a representation that captures the core aspects of the user's style. In contrast, for knowledge-intensive tasks, the unique features of each document's compression are important because they hold specific details. Averaging these compressions can wash out these details, which may explain the drop in quality when using more documents. While this averaging creates a single representation that reflects the user's documents broadly, it fails to maintain the detailed information from each document. We believe this difference between the two task types indicates a wider trend in personalized skill learning and knowledge-intensive tasks, and we plan to explore more tasks in these categories in future research. Additionally, we think that improvements in compressing single documents through better settings, improved designs, or optimized weights will also enhance multi-document compression. Thus, our findings are not limited to the specific compressor architecture we used in this study, and future research may investigate other compressor designs.